everybody. Welcome to another episode of Hidden Forces with me, Demetri Kofinas. Today, I speak with Gavin Schmidt, a climate scientist who heads NASA's Goddard Institute for Space Studies in New York City. He's the co-author of Climate Change, Picturing the Science, and the 2011 inaugural awardee of the AGU Climate Communications Prize. What's driving the warming of our planet, the acidification of the oceans, the shrinking of the ice sheets, the rising sea levels, decreasing snow cover, and retreating glaciers? Weather is the prototypical complex system. Edward Lorenz, one of the pioneers of chaos theory, was a meteorologist. So why is the science of climate so controversial? In today's episode, we cut through the controversy and dive right into the heart of climate science. We parse through the data, explore the models, plot the predictions, and consider the implications and what they might mean for humanity in the decades to come. What are the feedback mechanisms of climate? How do we measure the impact of losing reflective layers of ice, exposing permafrost, or releasing vapor into the atmosphere? What does the cooling of the upper atmosphere tell us about the cause of global warming? And how will humanity respond to more extreme weather events, hurricanes, droughts, floods, and forest fires as our populations grow and the density of our coastal regions increases? And is there anything we can do to prepare? As always, you can gain access to reading lists put together by me ahead of every episode by visiting the show's website at hiddenforcespod.com. Lastly, if you're listening to the show on iPhone or Android, make sure to subscribe. If you like the show, write us a review. And if you want a sneak peek into how the show is made or for special storylines told through pictures and questions, then like us on Facebook and follow us on Twitter and Instagram at Hidden Forces Pod. And now, let's get right to this week's conversation. So, Dr. Schmidt, welcome to Hidden Forces.
Thank you very much.
I'm very excited to have you on the program.
I'm excited to be here.
It's a little late considering the hurricane season. It would have been more news timely. I actually wanted to do something on climate change and global warming for a while. But like everything else on this show, I want to make sure that we have the right guest and that I'm properly researched. And it's interesting. So I cover a wide variety of topics on this program. Complexity runs through many of them. And in fact, we sort of embrace complexity on the program. And I rank each show in terms of how I prepare for it, in terms of the difficulty and things like that. This was, in its own particular way, the most difficult, but it had less to do with the complexity of the subject and the difficulty of the science. It really had to do with I think, what makes this subject so difficult for everyone to encounter, which is the enormity of the message in the data. And I think that's a very difficult sort of thing to disconnect override.
That's absolutely right. I mean, the science and the details is complex. The system that you're trying to study is complex. The discussion about what this science means is complex. And so, yeah, you've got like 3 levels of complexity layered up on top of each other there. So, no, I feel for you.
Well, I should feel for you because this is your profession. So listen, before we start, I want you to give our audience, tell them a little bit about who you are and your background, and then I want to contextualize our discussion. But why don't we begin that way? Why don't you give our audience a little bit of a background about who Gavin Schmidt is, where you came from, what train you took to get down here? No, I'm just kidding. But go ahead.
Sure. So my name is Gavin Schmidt. I'm a climate scientist, and I now run a NASA lab here in Manhattan that really focuses on understanding climate changes, observing climate changes, and then working out what the impacts of those changes are going to be. And we look at all sorts of kinds of climate change. Back in the past, what causes the ice ages, what caused the Cretaceous to be so warm, but also what's been going on in the 20th century, what's going to happen in the 21st century. Now, I got to this through a bit of a roundabout route. I was a mathematician when I was younger, when I was doing my undergraduate. All I really wanted to do was maths.
What kind of mathematics?
Yeah, applied maths, but problem solving, things that had nice, neat answers, and it was pretty and aesthetically pleasing. And I realized, after my PhD, that aesthetically pleasing wasn't the same as something that you can actually get a job with. And so I worked towards, doing more stuff that was of more interest to more people. So I started off doing ocean studies, which is more interesting.
The oceanography?
Yeah, that's more interesting than pure mathematics. And then ocean led to climate, and first of all, simple models, and then more complex and more. And like now, we work with the most complex models there are.
And you've been at Goddard for 20 years, is that correct?
About that, yeah. 96, I came here. Yeah.
And you took over for Hansen about 3 years ago?
Yeah, so James Hansen was the previous director. He'd been there since the early 80s, and he retired in 2014, and then I've been the director since then.
So audience, Dr. Schmidt's done a good deal of media, and I suggest that you Google his name on YouTube, and you'll be able to find some interesting talks, including a TEDx talk, which he gave.
Oh, TED Talk, not TEDx.
Oh, TED, I'm sorry, TED. That is a difference. No, you're very correct for pointing that out. I apologize. We had our last guest was TEDx, and that intro was in my memory, so
it's okay. Not all TED Talks are brilliant, and
no, you're
TEDx
very correct for pointing that out.
So.
It is an important point. So here's kind of my thinking. We've done one previous, and I should also mention to anyone who's new to the program, we did an episode with Brian Arthur, I think it's episode 8, on complexity science. If you're interested in understanding the science of complexity, you can go to that episode. We also did an episode recently with Daniel Dresner on this sort of thought leadership and the politicization of thinking and sort of intellectualism and the sort of the attack on experts, etc. And I think, one of the things that I try to do with every subject, and especially with this one, is I want to really break from any kind of advocacy here. I just want to talk about the science, and science, not the quotation science, which is what we sort of, but I want to talk about the data. I want to talk about the models. I want to talk about the predictions and the projections and the forecasts that come from all that data and from those models. And then I want to talk about what the implications of that are, assuming that we sort of prescribe to it. And I don't want to push that on anyone else. Everyone is up to themselves if they want to understand this or not. But I think it's important to understand it, because I think understanding it helps to. I'm actually not a believer in, if thermometers work, we should just believe it. If you don't have it, you should try to understand everything possible. So sure. Let's begin with that. And before we do, I also want to take a quote of yours. It's something I've been doing recently, which there were a few that I really liked. One is, models are not right or wrong, they are approximations. The question you have to ask yourself is whether a model tells you more information than you would have had otherwise. If it does, it's skillful. I think that's super important, right, to begin our conversation, which is science is not a fact. Science is an evolving empirical methodology for understanding the world. It's an approximation, and we have to understand that, because I think it's held to unfair standards. All right, so let's begin. The first question I want to ask you is, what is the relevant data that climate scientists are looking at? Like, what are the inputs that you think about when you're sort of building your models?
So it's very multifaceted. So the kind of things that people see in the public discourse about this are changes of temperature in the oceans and on land, changes in the amount of carbon dioxide in the atmosphere, changes in the solar activity over the last few decades. You can find all of this data online. But the real data that tells us what's going on, or that really gives us insight into the processes behind this, is actually much, much more voluminous and much, much more diverse. So NASA, we have about 20 satellites that are in either polar orbit or in geosynchronous orbit that are measuring everything from groundwater changes, ice sheet mass changes, ozone levels, temperature levels, the wind speed on the ocean, the amount of water vapor in the atmosphere, the amount of aerosols in the atmosphere. There's a small particles in the air, dust and soot and things like that. The amount of clouds, the amount of radiation, and it's through putting together all of that very, very disparate data and then connecting it to the processes that are the things that give rise to those changes. So convection in the tropics. So it's hot at the bottom, and you get this big, massive clouds that changes the radiation, changes the cloud, changes the rainfall. That's one process that has this kind of multivariate expression, or this multivariate fingerprint. And what we're trying to do with the satellite data, with the weather forecast data, with the ground observations, is really pin down what's going on in those processes. once we've done that, we can bring those things out. We can encapsulate them in code. We can approximate them as best we can. And then we put those into simulations. Now, those simulations are used for weather forecasts. They're used for climate predictions. They're used for attribution into the past, for exploring just how things connect each other. But that's where the complexity comes in, right? It's not
in the translation.
It's in the translation of those huge data sets that measure everything, and then trying to kind of pull out of that what the processes are that are important, right? And we use our physical intuition, we use ground measurements, we use satellite measurements, we use, we have airplanes that fly in between, measuring, looking down and looking up, just in order to be able to say, well, why does convection occur when it does occur? When does a cloud form? When does a cloud dissipate? When does it start to rain? When does it not start to rain?
So are you looking at correlations, and then all the set of correlations, then you're saying, okay, let's investigate these correlations and try to... how do you do that? What's that process like?
Well, it's not quite like that.
Not so neat.
No. So, we partner, for instance, with the Department of Energy, and they have these sites where, they'll just sit somewhere and measure everything that they can possibly measure in a column. And they do it in areas where we think something interesting is going to happen, right? So a front comes over, and then we see, it's dry here, it's wet there. Okay, when did the clouds form? When did the rain come in? How much did the radiation change? Was there a change in the ozone? Was there a change in the dust? And then can we simulate that? Can we understand what happened? Can we understand that sequence just from our physical understanding, from our physical intuition, which, over the years has become pretty good. And you just go around trying to find more and more cases that test your models. Now, your models can be, they're really great when it's something very clean happening here with nothing else going on, and they work fine. But then suddenly you've got something else comes in, and it's a little bit more confusing, it's a little bit more complex, and now your model fails completely. And so those are the kind of opportunities we look for. We say, okay, well, we can make the model better. We can do a better job with that trigger for understanding when convection starts, for instance.
Well, we're going to get into that because I want to get into details of how you formulate these models. Mm-hmm. Before we do that, how reliable is the data itself?
Well,
the instrumental data that we have, before we even get into sort of the proxy data.
Right. So, all data is collected by humans or by machines that were built by humans. And of course, we're all imperfect. If you're looking at historical data, then things have changed for all sorts of reasons that you wouldn't have ever designed to have them change. But they changed because there was a war, and then people moved this over here. And then, that building burnt down and they moved their instrument to the airport. All of these things happen.
Sure.
You get somebody who's really, really lazy, who's tasked to get up at 5 o'clock in the morning to record it, and they never do, and they always write the same number in.
Right.
So you have data that is imperfect.
Sure.
There's no question.
But an imperfect data is not going to tell you that the ice sheet is melting. Right? I mean, so like within the bounds of reasonable reliability.
What you look for is consilience. What you look for, different sources of data, different kinds of data that point you towards the same thing. Mm-hmm. Right. So if you've got 1,000 weather stations and they're all telling you the same thing, then it doesn't matter that one of them was run by a drunkard who never got up at 5 o'clock in the morning. Right. If you have observations on the ground that tell you that the ice has dropped by 100 meters in the last 50 years, and then you've got a satellite that says no, there's less mass there than there used to be. Okay, you've got a consilience of evidence, and so you can have some confidence to what's being.
Let's talk about some of these instrumental measurements, because some of them are really cool and interesting. Mm-hmm. One I actually learned about with respect to the drought that's going on in California, and I think it also applies to the ice sheets and the mass of ice and the poles, which is the use of lasers in order to determine the change in gravity. Could you explain to our audience a little bit how that works and the science behind that? It's very fascinating, and the technology.
Right. So you're right. This is a totally fascinating technology, and what you're talking about are the GRACE satellites, which unfortunately have just been decommissioned.
Is that right?
Yeah. So
when did that happen?
They stopped working on October 12th, and there was an announcement today, actually.
Why was that?
Because they've been in orbit since 2003, so that's 14 years, which is about 3 times their design lifetime. So the batteries that allowed them to store solar energy when they were in the sun and then use it to
transmit. And they haven't been repaired.
Well, they can't be repaired.
Oh, okay.
So once
because they're satellites.
Yeah, once things go into space, there's very, very few satellites.
Are they going to
be?
Are they going to be replaced?
So there is a GRACE follow-on mission that's slated to be launched next year.
Okay.
So it was an absolutely, I mean, you're right to highlight that. It was a great data set. So the idea is that there are 2 satellites, and what they do is they measure how far apart they are from each other. And as they're going over the planet doesn't have an even gravity field, right? So where there's a mountain, there's actually a little bit more gravity. You're tugged a little bit closer to the Earth where there's a mountain, and over the ocean, you're tugged a little bit less. And so as the satellites go over a mountain, they would be tugged a little bit more. They would come a little bit closer together. And then over the ocean, they would separate out by tiny, tiny amounts. And so the technology that allows us to measure exactly how far apart they are is incredibly precise. And what that allows you to do is to get a sense of, where the gravity hotspots are and where, that's very neat. But the neatest thing was because they were in orbit for so long, right? So since 2003, they've been able to show us where gravity has been changing. And you think, well, gravity doesn't change. But you're wrong. Gravity does change. And there's 2 main reasons why gravity is changing on Earth right now. One is that the ice sheets, particularly in Greenland, are melting. And so ice that was there, mass that was there, has melted and has gone into the ocean. And so that's a change in mass. And it's large enough that we can register it by using instruments that are measuring the total amount of gravity. Places where we're taking out a lot of groundwater. We've taken out so much groundwater, in fact, that there's less gravity. I mean, it's not like
it's remarkable.
Yeah, I mean, it's not like people are walking like they're on the moon or anything, but it's a detectable signal that we can see in these things, and you can see it in California, you can see it in India, you can see it in China. There are places where we are totally unsustainably mining the groundwater, and that's problematic.
And that's directly related to climate change because droughts require a certain.
Actually, it's more related to agricultural policy.
Well, that's what I mean. But that's what I mean. I mean the fact that there's drought in California and the desire to continue to use that water, they're pulling it from the water table. And,
right, but
they're using it to.
But a lot of California is arid anyway, and so they've been mining this since the beginning. It's not because there's a specific drought. It's because there just isn't enough water for the agriculture.
Okay, interesting. I was going off entirely off of a 60-minute piece where that was the implication. So they've been pulling from that water for decades, is what you're saying?
Yes.
Wow.
Yes,
remarkable.
Yes. And in a way that's totally unsustainable. And it's not just in California, but it's something that you see worldwide.
That's a perfect example of. We run a capitalist system, but we're not able to price everything, and that's a perfect example of an externality that weren't priced in the correct manner.
Right. So, yeah.
Because you can't replenish the groundwater.
Well, you can, but it's very, very slow. So for it to be sustainable, you can only take a small amount of groundwater out. And the older the groundwater is, the slower it refreshes, and so the less you can take out sustainably.
And one could argue that in the future, it may be much more valuable to have water to use to sustain, edible food as opposed to wine crops.
I like wine, so I mean, let's.
I'll tell you what. I'll tell you what. I put it this way. I love wine.
Right.
I might get some wine after this interview, but I think when we talk about what we're going to speak about today, and we look forward in terms of time horizons, these are perishable resources. And water is obviously not a perishable resource, but potable water is. And so, I think this is really about what are our priorities. I think this is central to our conversation. So that's instrumental data. Talk to us a little bit about proxy data, because that's important, because your data set is formed by instrumental data, which is the data that you're able to collect pretty much since 1800 or 1850, something like that.
Yeah, so if you're looking at weather stations that are networked across the world, you can go back to about 1880, 1850 and still get a good sense of what the whole planet was doing. If you go back further, then you've only got a few stations in Europe or in the US, and that's not enough to give you a kind of global picture. But we still have a good idea about what happened across the world in times past, right? So we know that there were ice ages. We know that there were hot periods millions of years before that. We have a pretty good idea of what the history of climate on the planet is. And that comes from what you said, proxy data. So these are measurements that aren't direct temperatures, but they're things that were related to temperature. I mean, they can be kind of coarse, kind of geomorphological things. Like, so, you can see a moraine, like the end part of a glacier, right? So, we're in New York City. Brooklyn in Prospect Park is the end moraine for the glacier at the last glacial maximum, right? So about 20,000 years ago, the glaciers came all the way down from the Arctic Circle across Canada, and they stopped in Prospect Park.
That's interesting. So how do we know that?
Because you can go there. I mean, if you kind of stand at the top near Grand Army Plaza and you're looking down, you'll see a little kind of ridge of small hills. That's and you dig into that. It's all glacial till. So it's a feature that you get when the glaciers kind of push all of the stuff in front of them, and then when they stop, there's just a pile of rubble and things like that.
And how long ago was that?
That was about 20,000 years ago.
That's amazing.
Yeah. So you can see that in the landscape. Right?
Wow.
You can see where the shorelines used to be when the sea level was higher or lower. You can see in the ocean mud, there are geochemical traces that you can measure. There are kinds of animals that lived when it was warm or when it was cold, and you can kind of piece together the history of the climate on the planet. And the different and diverse ways that people have got clues about past climate are really very impressive. There's one guy who goes to the high Arctic in the springtime or in the summer, and what he looks at is as we're losing ice, right? So there's a lot of places where it snowed at one point and then it never melted, right? And then, but as it's melting now, what it's revealing is the mosses and the plants that have been underneath that snow and
permafrost.
ice. I mean, there's permafrost underneath it, but there are mosses and things, and they died when the snow fell, and so they keep track of the carbon. They can be carbon dated, and so you can go back and you say, well, how old is that thing that was just covered in snow? And you get some stuff that's like 1,000 years old. You think, oh, okay, that's interesting. So it was there when it was 1,000 years ago, then it snowed, and now it's being revealed again. And then there's other stuff that's like 4,000 years old, and you go, okay, that's interesting. There's other stuff that's like 10,000 years old. You go, oh, okay. And then there's stuff that is so old that there's no radiocarbon left in it. And that means that it's at least 50,000 years old. And what it actually means is that it probably comes from the last, what we call the interglacial period, which is about 125,000 years ago. And that was the last time that was uncovered. And so we're finding places where the melt that we've caused is the biggest thing that's happened somewhere in 100,000 years, right? So that's kind of important.
Right. And we'll get into sort of, why you believe and I believe, and I think that,
well,
I don't think
we don't believe. We look at the data.
Yeah, exactly.
And, you find what explains the data to the best of its ability.
I agree. I'm trying to find a way to say this because I really want to give people, I don't think that there really are going to be many in my audience that question this, but for any listener, I don't want it to be pushed on them. I want to find a way for people to actually try to learn as much as possible from this conversation, which is why I tried to state it that way. So let's talk a little bit about the drivers of climate change as we know them, like the Earth's orbit and solar cycles and the ozone, etc.
Big
and greenhouse gases.
The continents shifting around, changes in ocean circulation, massive asteroids coming in and destroying everything. All of these things have happened and have changed the climate. Evolution has changed the climate. Before there were land plants, the climate was very different. Before there were blue-green algae, the climate was very different. So the kinds of things that can change the climate are enormously diverse. But they don't all happen at once, right? We know, for instance, in the 20th century, there wasn't a really big asteroid impact that, caused everything to go extinct. We would have noticed. But we do know that we increased the amount of greenhouse gases in the 20th century. We do know that we increased the amount of air pollution in the 20th century. We know that we chopped down a whole bunch of forests. We know that there were a few big volcanoes that went off. We know that the orbit of the Earth didn't actually change that much. We know that the sun had, kind of these quasi 11-year cycles over that entire period, and maybe a little trend as well. We know that we changed the ozone layer because of our use of CFCs and other ozone-depleting chemicals. So what we do, for any particular period that you might be interested in, is you think about all the different things that could be going on. The orbit, the volcanoes, the sun, the greenhouse gases. And what you do is you try and calculate the fingerprint that's associated with just that effect. And they're not all the same.
I'm trying to isolate the variables.
Yeah, so you're trying to that's exactly right. There's a lot of different things that are going on. What does the fingerprint of each of those changes look like? Just calculate independently, assuming nothing else is going on. And what happens is that they're very distinct. The fingerprint for changes driven by the sun are that it gets warmer during the day and not so much at night. It gets warmer all the way through the atmosphere from the surface all the way up to the mesopause. But if you look at the change from greenhouse gases, right, now greenhouse gases are a kind of a blanket over the Earth. They stop radiation from escaping from the Earth. And so that's something that happens, all day and
Let's
at
talk
night
about
as
that a little
well.
bit. I want to get into the science of the greenhouse effect.
Okay.
Let's talk about that. Let's
Sure.
explain that a little bit. And I want to also talk about it because there's a really great example in the science that I think helps people understand it, which is the difference in temperature gradients in the upper atmosphere versus the lower atmosphere, why that's actually a perfect explanation or is easily explained by the greenhouse effect.
Right.
So why don't you just tell our audience a little bit about this?
Okay, so the greenhouse effect is what really makes life possible on this planet at all, right? So this is something that was worked out by Fourier in the 19th century, by John Tyndall, who worked out what the gases that were involved. It's very old science, and so the idea is that everything gives off heat. Right, so you're sitting across from me now. You're radiating about 100 watts of energy right now, and it's mostly coming from your head. If you had an IR camera, you'd be able to see your head kind of glowing yellow, and pretty much nothing anywhere else. And everything radiates, like the chair that we're sitting on, the table radiates, the earth radiates, the tree radiates, and so anything that has a temperature radiates. Now, if you're a planet, you have some energy that's coming in, right, from the sun or from your star, and then for your planet to be stable, the same amount of energy has to be leaving. And the same amount of energy is leaving, and it has to leave in the wavelengths that you're radiating, and that depends on your temperature. So that kind of infrared radiation for the whole planet is kind of going off.
The science of thermodynamics we're talking about here.
Exactly.
The same science that accounts for why we're able to determine the temperature from a thermometer. Well,
Kinda.
the dissipation of heat that expands or contracts the liquid? No.
Well,
All right.
Kinda.
I'll
Anyway,
stop. I won't venture into that area.
Okay, so your planet basically has this energy balance. The sun's energy comes in, this infrared energy goes out. But greenhouse gases get in the way, right? Literally, they get in the way. So most of the air in the atmosphere, it doesn't care about infrared radiation. So if you have an atmosphere that was pure nitrogen or pure oxygen, then the radiation from the surface would just go straight out to space and there'd be no interaction. But other gases have very specific absorption lines, right? So they absorb photons that have a particular energy. Right, and so carbon dioxide and water vapor and methane and nitrous oxides, they absorb energy kind of by coincidence at the same frequency that the Earth is giving it off. Right, so the absorption bands for carbon dioxide are right in the middle of the spectrum for the Earth. And that means that instead of the energy going straight out to space, it gets absorbed in the atmosphere. And when it gets absorbed in the atmosphere, it then re-radiates in both directions. And so it's like you've put an extra blanket on. Right? It's hard for that energy to get out. And so when you add to that blanket, you put in more water vapor, you put in more carbon dioxide, you put in more nitrous oxide, it becomes ever harder for the Earth to get rid of its energy.
That's a good metaphor you're using. So a blanket, like putting a blanket on when you're in your bed.
Right. So the blanket is not a heater, right? It's not actually producing heat, but it keeps you warmer, right? So that's exactly what these greenhouse gases are doing. And adding more and more carbon dioxide in the system is like piling on the blankets. And so, you have to heat up more in order to kind of get past that barrier. And so the surface temperature increases in response to that.
You mentioned water vapor there, and you had mentioned permafrost earlier. Both of these are have important feedback effects in warming.
Yeah.
Why don't we talk about that a little bit more before we get into the models, because I don't want to forget about that.
Okay. You're absolutely right. Those are what are called feedbacks or amplifying factors.
Which for me, and please tell me, those are for me the scariest because they're the non-linearities in the system of climate change.
That's right. I mean, these things can be non-linear, but
which are very difficult to predict, right?
Well,
Non-linear effects.
Yeah, so that's obviously true, right? So things that are linear and just like smoothly increasing, those are relatively easy to predict. When you're going to have things that have big sharp thresholds or kind of exponential growth, then it is much more hard to predict. That's very true. But it's very important to understand that there's lots of different feedbacks in the system. So as the temperature increases, what happens is that the capacity of the air to basically soak up water also increases. So for a 1 degree change in temperature, you get about a 7% increase in how much water the air can hold. And that means that, we've actually gone up by about 1 degree Celsius since the 19th century, about 2 degrees Fahrenheit. And so the amount of water vapor in the air has also increased. And it turns out that water vapor itself is a greenhouse gas. It also produces clouds and rainfall and more intense rainfall. but it is itself a greenhouse gas. So the more water vapor, the more carbon dioxide you put in, the more water vapor that emerges because it's got warmer, and then it gets warmer again because the water vapor itself is a greenhouse gas.
How significant is water vapor among the different sort of feedback mechanisms?
It's the biggest feedback mechanism, so it's really important.
Right.
Yes.
And can you tell us a little bit about permafrost and how that's relevant? And actually, let's also talk about the ice sheet and the reflectivity of the ice sheet.
Okay, so that's another great example of an amplifying feedback. So you've got a lot of places in the north that are covered in snow or in sea ice or in ice sheets. As the planet warms up, that snow melts. It reveals either a dark ocean underneath it or the darker ground underneath it, and that absorbs more solar radiation, and so that warms up more than it otherwise would have been. So that kind of ice albedo feedback, which is also one of the reasons why the Arctic, for instance, is warming up faster than any other part of the planet.
Because it has...
Well, because the planet is getting warmer, the ice is melting, and that means that more solar radiation is being absorbed, which means that it's getting warmer and more ice is melting.
And what about the permafrost?
So permafrosts are regions that have kind of like deep layers of frozen ground. And what's happening there is that a lot of that some of it is a relic from the last ice age. But other things that, they've been permafrost there for millions of years. And what's happening now is that we're warming up. And so that permafrost is melting, it's disintegrating. And the carbon that was stored in there, a lot of it was peat, organic matter, is now oxidizing. And it's becoming more carbon dioxide, more methane, all of which are greenhouse gases, all of which are then adding to the problem that started this.
Yeah, those are like carbon bombs, right? No?
I mean, so there's been a lot... some numbers that have been kind of thrown out there in the literature which aren't really very well based. So this talk of an Arctic methane bomb from permafrost is rather overblown in my opinion. So
let me rephrase what I'm saying, or let me be more detailed. The way I view the feedback mechanisms like the ice sheet and like the vapor is that they're smoother in a way. There's something about the permafrost that just feels like you just get a big burst of it. Is that incorrect in my thinking? Or is it really irrelevant?
No, it's not. It's not irrelevant, but it's one of many factors that are causing the carbon cycle to change or causing the hydrological cycle to change. We started off with this notion of complexity, right? Mm-hmm. So the fundamental issue when you have a complex system is that pretty much anything you change eventually kind of feeds back and causes it to change. And like some of it will cause it to dampen, some of it will cause it to accelerate, and it's the balance of those things that give you those kind of emergent patterns that you see.
Non-equilibrium.
Right. I mean, it's kind of quasi-equilibrium, but it's non-equilibrium locally. But the whole thing is like kind of a statistical equilibrium.
How detrimental, for example, I'm pretty ignorant on this subject, but that's why I don't really go out and pontificate on it. Mm-hmm. How detrimental is the pontification of advocates for environmental change on behalf of climate change? How detrimental is it that you have many people going out pontificating and making specious arguments based on a manipulation of the facts when they don't really have to, if they just understood the science, we'd all be better off because we could just all have, there would be credibility in the community. There are people that, in other words, what I'm saying is there's a phenomena that I experience, which is that I see that in subjects I care about, that there are people and the institutions or whatever that poison the well, and so the skeptical community within it and that point to those and say, look, XYZ is saying this and that, it's not true, and then it just destroys the entire sort of edifice of argument and science.
Okay, so I recognize the picture you're drawing.
The reason I even mentioned it is because I'm sitting here and I'm saying certain things and I see your hesitation with some stuff, and I'm just saying, well, it's a good thing I'm not going out and pontificate on this. Okay.
So in any topic, there are people with louder voices than their knowledge would justify, right?
Right.
And that's true for any topic, right? And you can find communities or Reddit lines where people are just bullshitting the entire time. Mm-hmm. What makes it more problematic with climate is that those fringe voices are kind of weaponized by people who have political agendas that prefer that we not pay any attention to what's happening to the earth. And that's really the issue. It's why these people have a megaphone, why these people have a TV station, why these people get flown all over the place to present their arguments or to testify in court cases or to testify in committee hearings in the House. How does that happen? right? That doesn't happen because there's somebody loudly, tapping at their keyboard in their mother's basement. That happens because it's politically convenient for people to have, kind of sand thrown in their eyes when there's a topic that people don't want them to focus on.
Money in politics.
Money in politics, there's no question.
There are large business.
And the vested interests associated with, oil and gas and coal are well entrenched and powerful. I mean, but there's still a role for clear discourse, though. Right? And it's not because there are people who are pontificating and talking nonsense that we have to have a discussion. We have to have a discussion because this is a really important topic. Right? We have to have a discussion about this because we are implicated in causing this problem, and we should understand what those consequences of our actions, both individually and as a society, should be.
It's interesting you say that. I want to make one point, then we'll move to the models. Mm-hmm. One of the arguments you hear is that, by people who believe that we should act on climate change, is that, irrespective of the cause, we should do X, Y, Z because the Earth is warming, and we can all agree it's warming regardless of what the cause is. But I actually think that understanding the cause is part and parcel of understanding the solution, because if we recognize that we are causing the warming, then A, we have some credibility, and B, we know what we can do to fix the problem because we would be causing it. What do you think of that?
So I agree with you. The idea that just because the planet is warming, but we have no idea why, therefore we should reduce carbon emissions, makes no sense to me at all. You reduce carbon emissions because carbon dioxide is the driver of the warmth, right? Otherwise, why would you bother? There's lots of things that we could do that would make our lives better, that we could have more efficient cars and better insulated buildings. These would be good things in and of themselves, but they also reduce greenhouse gases. So you might say, well, let's do these things here, and I don't really care about what happens to greenhouse gases because I don't understand it. But it's better to understand why things happen, and then you can actually choose to do things that make a difference as opposed to doing things that just make you feel better.
So let's talk about the modeling now.
Sure.
So what is a climate model? What are some of the earliest sort of weather or climate models that we've had, and how have they evolved over the years to where we are today?
So we just had the 50th anniversary of the first real climate model that
Manabe and Weatherland.
Weatherald. Yes, which was published.
Thermal equilibrium. What do I got here? Thermal equilibrium of the atmosphere with a given distribution of relative humidity. I actually looked it up to find what
that even means. Yes.
Yeah.
But what they did was this is the first real climate model that had all of the things that you need in terms of working out what happens to radiation when you change the amount of carbon dioxide. The relative humidity term there was they were saying, well, we don't really know how the water vapor part is going to change, so we're just going to keep that fixed. And, it was a reasonable approximation, though it wasn't perfect. Right? We're doing a lot better now than we did 50 years ago.
It was much simpler. The computers that we had for working it out were much less powerful. You could run that model on your Apple Watch. I mean, they're using punch cards for that.
Probably. Oh, yeah, and this is all done in punch cards. No graphical user interfaces or anything. And they made a number of predictions. They made a number of predictions for what they expected the surface temperature to be after 50 years. They expected that it would warm at about the rate that it has. They made a very interesting prediction, which you kind of alluded to before, was that as carbon dioxide increases, the ground would warm, but the air aloft, kind of above 15, 20 kilometers, would actually cool. And this was before we'd made any measurements of trends in the stratosphere. And they said, well, it's because of this very special thing that happens with carbon dioxide. So the reason why the stratosphere cools is a little technical, but effectively in the frequencies that carbon dioxide likes to absorb in, there's so much carbon dioxide below that almost nothing gets through at those frequencies. And then when you add more carbon dioxide there, it just radiates, because radiation and emission are the same physical phenomena, but so it radiates more and so it cools. And that was a prediction that was made well before there were any measurements of the trends. And what's happened is that it's become abundantly clear that we're seeing this cooling, not just in the stratosphere, but in the upper stratosphere and in the mesosphere and in the thermosphere. All of these things are cooling because of the increased amount of carbon dioxide, which is opposite to what you would have got if the warming had been from the sun, for instance.
How many orders of magnitude can we currently model with our climate models?
Right. So what we do with the climate models is you take the planet, right, and then you kind of chop it up into little bits until you basically fill up your computer. And the level at which you can do that detail is changing every decade. We can do more and more details.
So you're starting off at the most macro picture, and then you start to get more and more refined and detailed.
Right. So if you think, well, we're only going to do the globe, let's just average everything and just make an equation for the thing. Okay, well, that's very simple. That was done many, many moons ago. So, okay, well, we can do better than that. Well, let's split it into hemispheres, north and south. Let's split it into latitude bands. Let's split it into grid boxes that are only a few hundred kilometers or maybe 50 kilometers square. And you can, in each of those cases, you can add in more and more detail, and you get more and more complexity, right? Once you get below about 1,000 kilometers, you start to see weather systems, right? You didn't get that when you were doing like 4,000 kilometer boxes. When you get to 4 kilometer boxes, you have convection just kind of spontaneously happening. But at every point, you have to stop, right? Because the computers aren't infinite. And that point at where you stop, like the kind of cutoff distance, you then have to kind of make approximations for everything that's happening at the smaller scales or that is happening very, very fast. And what we're doing as computers get better is we're kind of encroaching into that small, fast area of physics to make better and better approximations.
Are the computers the bottleneck? Is the processing capacity the bottleneck here? What are the bottlenecks, if we can think of it that way?
Right. So, I mean, we generally kind of use whatever computing we have, and that's been increasing dramatically over the last 20 or 30 years. So we've been able to do better. But, our understanding of the processes and the observations, like all of these things actually go hand in hand. If you gave us 1 million times faster computer tomorrow, right, we wouldn't be able to use it really, really effectively because we wouldn't have set up the observational programs, the analysis programs that would allow us to fill in the detail, those extra scales that we have to do. So one of the nice things is that the science it gets better on all these fronts, pretty much simultaneously. So we have more detail in our understanding, we have more detail in our processes, and we have more capacity in our computers pretty much at the same rate. And that allows us to kind of, keep things balanced as you go forward.
So, there's been a huge revolution we've covered on the show in multi-scale biology and genomics and certainly in financial markets with big data analytics, but also machine learning and artificial intelligence. What role is that playing in climate science?
That's a great question. And I'd have to say it's not playing the role that you might have thought possible. And maybe it's because it's still early days. But the topic that we're dealing with, climate, is the archetype of a multi-scale system, right? You've got things that are happening at the micron level, cloud formation, the microphysics of a cloud droplet that matters for radiation, for rainfall, for all sorts of things. And then, all the way out to, massive weather systems or hurricanes, they're really, really large systems, or the circulation in the ocean. And we're generating, huge amounts of data. I mean, big data is really like our number one problem. And so you'd think, oh, well, let's throw in some machine learning, see what's going on, see if it can recognize, patterns that we haven't seen before. But what tends to happen is that the people that come in with the machine learning come in with algorithms that they worked on with Facebook and with Apple and with Google, and they say, well, can we apply these algorithms to your problem? And you go, oh, man, it's not really a recognition problem. It's not a, it's not a ranking problem. We're trying to find like physical processes. And there is a community that I've been part of that's trying to like kind of make a conversation between the people that are coming in with these tools and with these skills and people who understand the system and trying to apply it. But it hasn't really clicked as yet.
What about the community of game developers and engineers? That seems like one area where you could possibly find some synergy. Because there are commercial applications to developing simulations that run on things like Unity or whatever.
Okay, so here's a slight problem that comes in GPU chips, right? Very fast, would nominally allow you to do a lot more calculations than we can do with a normal chip. But they were developed for games where, it doesn't matter if it gives you the same answer all the time, right? So they're actually pretty error tolerant, but they produce a lot of errors, right? But you can't have that in a scientific application, because if something goes wrong and then it just goes bleh, and you go, oh my God, the model crashed, what's going on? But then it does a different calculation the next time you run it, then you can never debug anything.
I see what you're saying.
And it really matters that you can be able to do that with scientific codes. And so we've never been able to use GPU technology. And like now, they're much better at error correcting than they used to be. But at the beginning, it was, no, we just can't use that technology. And so you say, okay, well, there's all this computing that you can do, but it doesn't fit. And we're not a large enough community in and of ourselves to get people to build chips just for us.
That's really interesting, because there's such a revolution that's going on in computer science and in technology. And, speaking of that, and I wanted to get into this towards the end, but we might as well touch on it now. How realistic are some of the potential technological solutions that go beyond renewables, but that actually have to do with sequestration or with actually extracting greenhouse gases? I mean, what's the field there?
So there's a number of different things that people are pursuing. So one of them you mentioned there is air capture. So you capture from flues or from ambient air the carbon dioxide that's in it, and you try and bury it somewhere. So in theory, there's no problem with this. The chemistry is well understood. How you can do that with enough energy to kind of, you have to kind of lower the ground state of the carbon. You have to put energy in to do that. It's fine theoretically. The issue is, how much does it cost and does it scale? So the problem is that it costs too much money. Right. So you might have heard people talk about the cost of carbon, or the social cost of carbon. How much, what a carbon tax should be if, the damages were to be taken into account. And the numbers that people come up with, $40, $60, $100, something like that. So that's pretty much the price that you, in a perfect market, you would be paying to not emit carbon dioxide in the first place. But unfortunately, the cost of air capture is more like $600, $1,000 a ton of carbon, which means that you're paying way over the odds to remove it. And there's lots and lots of other things that you would do first that don't involve that. So the big problem there is cost. Now, there are more efficient ways to capture carbon, right? For instance, from a smokestack. I mean, not quite a smokestack, but through like the generation
pipe, at the source of the
right?
pollution.
Carbon dioxide is much more concentrated there. You can design it so that you get a stream basically of pure carbon dioxide, and you can say, okay, well, now I'm just going to capture that, and now I have to do something with it. And what people are doing are they're pumping it into oil wells and like kind of putting it back into the ground, but there isn't really quite enough space to do that for all of the carbon that you would want to capture. Some people are putting it into rock formations where it's actually reacting with the rock and making different kinds of rock, and that's a pretty permanent solution. Other people are saying, well, you can just pump it into the deep ocean, but that's also rather expensive and ecologically
and that's that contributes to the acidification of the ocean.
Yeah, so the acidification of the ocean is happening because we've increased the amount of carbon dioxide very, very quickly, and so the top layer of the ocean has become much more acidic than it used to be.
Can you explain what that means for our audience?
So the amount of ocean that's kind of being mixed by the winds depends kind of a little bit where you are and how strong the winds are, but it kind of ranges from, about the top 60 feet to, maybe the top 1,000 feet in the North Atlantic. And that's the part of the ocean that's always being mixed in with the air, right? So it's always being seen by the air.
Reacting with the air.
And carbon dioxide is like kind of coming in and out of the ocean at that point. But because of the chemistry of carbonate and the chemistry of carbon dioxide, the more carbon you put into the atmosphere, the more acidic it becomes, the smaller the pH. And so you've got changes. We've increased the acidity by about 30% in the last 100 years or so, and that's having noticeable effects on animals that make shells out of calcium carbonate. So oysters, mussels, crabs, lobsters, corals, those kind of things.
Well, I want to get into that towards the end when we sort of look at predictions. One thing I want to state, and we can actually probably get there right now, but one thing I want to state that I was thinking about when we were talking about these technologies is that at the same time, I don't want listeners to, and please correct me if I'm wrong here, but I don't want listeners to come away with the idea that even if we could just somehow extract the carbon from the atmosphere, extract however much we want, that certainly would solve the problem now. But there comes a point in time, it's just like I think about it in terms of like the melting of an ice cube on a table. it takes a certain amount of heat to melt a cube, but you can't just form that right into an ice cube again. In other words, if we get a certain amount of warming, we can't just reverse that. Right. In other words, there is a runaway warming effect. And you talked about the vapor. No.
Right. So, I mean, in practice, we're not going to go back to the situation that we had 150 years ago, right? I mean, the planet is still catching up with what we've done to the atmosphere. We're not slowing down.
When you say we're not going to go back to where we were 150 years ago, we're not going to get...
so we're not going to get back to the temperatures that we saw then. I mean, so the choices that we have in practice are, do we accelerate this global warming trend by burning more and more and more fossil fuels, or do we try and bring down the emissions and then it's only going to warm a little bit more? Right.
And
so, like stopping global warming or reversing global warming, those are no longer on the cards.
I think something else is important. I want to say this again in my own words, and please offer your opinion on this. I think it's important for us to contextualize our conversation with the understanding that we're living in a world of exponential population growth, and growth not just exponentially in the earth, but in the low-lying areas. I mean, we've built a society around a particular sort of stable climate.
Right.
And that's why I think this is so relevant.
Okay, so you're absolutely right. That's exactly why this is an issue. The issue is not, what's the perfect temperature for the planet, or what's the perfect level of carbon dioxide. None of those things are really sensible questions. The question is, what have we built our infrastructure with the expectation of? And how is that expectation changing?
What are we adapted for, both biologically and technologically?
Well, biologically, we can adapt to a lot. We have people living in Dubai and people living in the high Arctic. So, physiologically, we can cope with a wide range. So that's not really the issue. But the issue is that we have built a society based on expectations about climate. How close to the shore do you build your houses? Where do you build your agricultural infrastructure? Where do you build your trains? Where do you build your cities? And all of these things have basic expectations about, what sea level rise is going to do, what storm surges are going to be like, what extreme weather is going to exist.
Extreme, that's a great point, right? So it's the extreme events that are the concern, because in complex systems, it's the outliers that create the most damage, right? That's what we need to be worried about.
Yeah.
So let me ask you this. In the interest of time, let's just get straight to the projections that our current models are giving for us, and sort of what we can understand in terms of best case scenarios, worst case scenarios, taking into account what we may or may not do to influence all of this.
Right. So when we're going forward, there's this target that the Paris Accords talked about, this 2 degrees of warming above pre-industrial. But nobody really understands what that means. Like, what does 2 degrees mean?
Celsius.
2 degrees Celsius.
Which is
plus, nobody knows what that means. Right?
4 point what?
It's just under 4 degrees Fahrenheit. But then, that doesn't seem like a very big number. But in terms of the planet, it's a huge deal, right? So we mentioned the Ice Age earlier on, right? How cold was the Ice Age compared to today? It's only about 8 or 9 degrees Fahrenheit colder. Right, so 4 degrees Fahrenheit warmer. That's halfway to an ice age, but in the other direction. And the worst case scenarios are like a full ice age unit in the other direction. And you think about how different it was during the Ice Age. Where the ecosystems were, what sea level rise was doing, what the ice sheets were doing, what the temperature was. All of those things are massively different.
And the population of the Earth in terms of human beings was
much, much smaller.
Sort of fraction.
Yeah, I mean, so the changes that we saw at the end of the Ice Age, those are bigger than the changes we're going to see now. But we didn't have a huge investment in the status quo. If you're a hunter-gatherer and the sea level rises, you just walk.
That's 100% correct.
Right. But but if you're a hunter-gatherer living in New York City, then you're not going to do that. Right?
Or your sewage treatment plant is located in a city for 10 million people, and all of a sudden salt water comes in through the pipes.
And your outflow is like 3 feet above high tide level, and then it doesn't outflow at all once you've got a meter of sea level rise.
Or the fact that the bread baskets of the world are located in areas that get ample amount of sunlight and could potentially become dust bowls in this scenario. And it's not so simple to just move those farming communities up north where there's less sunlight.
But also things like soil, right? So everyone says, Canada will do well. We can go and grow our wheat in Canada. But the problem is that Canada has seen so many ice ages in the past that there's almost no topsoil. So the rich, fertile areas, there's a reason why they are where they are, and we can't just move everything towards the poles.
And the migration as well. That's one of the first impacts, right? The migration crisis that would occur as a result.
Right. Well, we can see a little bit of this now. after Katrina, lots of people left New Orleans. They ended up in Houston. After Harvey, a lot of people are leaving Houston. We can see after Maria, something like 70,000 people have moved to Florida. And you say, okay, well, that can be managed, but maybe it can't be managed, right? You look at Bangladesh and you look at the floods there, and now you've got hundreds of thousands, millions of people who are looking for somewhere else to go. That scares me. Not because
me too.
It's people moving. I'm a big fan of people moving,
right?
But it can get uncontrolled, and when it's uncontrolled, really, systems break down. We've seen systems break down in Puerto Rico. We've seen communication systems and power systems and sewage systems and water systems break down when the stresses are too high, and that's the thing that really worries me.
Well, correct. It worries me as well, and the way I think about that is that you don't want to be playing catch up. And it feels like that's sort of where we're going. We're getting into a place where there's a full court press on, and we're just trying not to lose. And that's really not a good place to be. It's not how you want to approach anything.
You want to prep. You want to be prepared. You want to be in a position where you're not surprised by the outcomes. And so one of the things that we do, and the science and the predictions that we make, is to try and get people to think about those worst case scenarios so that they will be prepped.
What do you think likely outcome is based on what the models are projecting and based on, let's say, what most political forecasters are forecasting in terms of sort of political outcomes and as well as potential commercial solutions that may come along, because we have had this sort of clean energy revolution, which is an exciting phenomenon. I mean,
right.
So what do the next 10, 20, 30, 50, 100 years look like? And if you want to sort of give a few, maybe best, middle, worst case scenario or something.
Yeah, predicting the future is hard.
It's really interesting. I'm sitting here looking at you, right? And I'm thinking, I'm coming, again, from a place of ignorance, as is the audience, but you're not.
Right.
You actually know way more than all of us, right? So you're actually, your feelings on this subject actually matter. So I'm actually searching your facial expressions to give myself a sense of, how do you feel? I'm curious to ask you this.
So sometimes I wake up and I see that there's been another round of bullshit and people like making things up in order to ignore the problem. And I think, we're never going to do anything. Then
how does that make you feel?
It makes me feel sad. Yes. I have a 2-year-old daughter, and she's just kind of getting into how her feelings are. And so she's kind of worked out when she's angry and when she's sad. So that's pretty much, how I'm seeing emotions at this particular moment. And then I see another story about, the penetration of solar energy in energy markets and the latest bid price for a wind energy plant in India or in Scotland. And I'm thinking, oh no, maybe we will turn it around. And then I see lots of non-joined up thinking, people that are trying to cost things without taking into the co-benefits of moving away from internal combustion engines. So even if carbon dioxide wasn't the problem, moving to electric vehicles instead of internal combustion is much, much healthier for everybody involved. It's healthier for the people who are working in gas stations. It's healthier for the people that live near main roads. It's healthier for people in the cities. It's healthier for crops because you're not putting out so much nitrous oxides, which cause ozone pollution, which reduce crop yields. There's an enormous amount of public health and productivity bonuses to be had by moving away from oil. And then you've got the climate thing, which really just adds to all of that. And it says, okay, this is a good thing to be doing. And you see some of the great technological breakthroughs, and you see the price of electric vehicles coming down. You see electric buses coming online and electric trucks coming online. You think, okay, no, we're making progress. And then you see,
pulling out of Paris, for example. You think that was I mean, certainly if you want to do something proactive with the climate, the stipulations within the accord were positive, but given the fact that it was non-binding and given potentially the positive effects of pulling out in terms of raising awareness, I mean, are there ways to sort of...
It's a bit of a backwards argument. I mean, there's a big difference between setting a target and actually doing something on the ground to make that target happen. Right. So I think we've got past the point where setting more targets is really helpful. We've got to the stage where people need to be demonstrating that they can make progress. And how do you make progress? Do you make progress with, technology incentives, with taxation, with mandates, with greater awareness? What of these things work? And the whole Paris process was really designed to help new ideas flourish, those new successful ideas to kind of spread around the world and be implemented in more and more places to kind of scale up what people can do and how fast they can do it. So, being part of the Paris process would help us do that as the US, and I think help the world move towards those targets more quickly. But,
Do you think that the devastation that has occurred in China, its air pollution to the environment, and their reaction, which has been to sort of strongly invest in alternative renewable forms of energy, coupled with their emergence as a leading sort of power in the world in a way, can actually be a significant force for progress in this domain?
Possibly. China is not a perfect society in any respect. And, the pollution problems there are just unbelievably bad. I mean, the number of people that are dying prematurely because of the air quality in Beijing and Tianjin or even in Delhi is enormous and deeply troubling.
Well, a lot of countries have been looking at that and have decided not to invest in coal as a result.
Right. But, their problem isn't just coal. Their problem is coal, it's factories, it's domestic burning of kind of low-quality coal, cars, nitrous oxides. And, one of the problems with China is that it's not a democratic society.
Right.
So a lot of the checks and balances that you would have in the US or in Europe don't exist.
Right.
So there's a lot of autonomy in the state operating enterprises. There's a lot of autonomy in the regional governments where the central government can say, oh, you should reduce your pollution. And they'll say, yes, we did that already. But nothing actually happens. The central government thinks that people are paying attention to them. Everybody pretends that they're paying attention, but nothing actually happens. Mm-hmm. So you've had cases where people have built new technology to clean water or to reduce pollution. Somebody from the central government turns up, they turn it on, everybody's very happy, and then as soon as the guy from the central government has gone away, they turn it off again because it's too expensive to run.
Well, we kind of covered some of those absurdities with Ann Stevenson Yang on episode 16, I think it was, on the Chinese financial system and banking system. And one of those examples is just the way in which the authorities and sort of the commercial interests would leave the lights on in the buildings because the analysts, the financial analysts, had decided that they didn't trust the original sort of occupancy numbers of the buildings, and so the developers started leaving the lights on to trick them, and then they just an incredible amount of waste because the number itself became the target as opposed to the actual sort of positive.
And that's the kind of thing that happens where you don't have trust and where you don't have checks and balances and you don't have a real democracy. So looking to China as a model to kind of save us in this situation is tricky because you can't really trust what's going on. So I'll give you another example. So the official statements about how much China emits in terms of short-term pollutants, nitrous oxides, sulfur dioxides, we can measure that from satellite, right? We know exactly how much stuff is in the air. Right. And then you say, okay, well, give us your numbers, and you put in their numbers and it just doesn't match. Mm-hmm. And so you know that their numbers are not accurate. Mm-hmm. And there's all sorts of reasons why it is. But the basic reason is that there's no democracy, there's no accountability, and there's no checks and balances in their system. So it's very hard to know what's going on.
All right, let me ask you this in closing, because I think rather than have you sort of do the typical sort of best case, worst case, you mentioned you have a daughter. Do you have just one child?
Yes.
Obviously, she matters a great deal to you, I'm sure.
She does.
And your family does. And as a father, you must feel some level of personal responsibility for her.
Yes, indeed.
So what are you doing as an individual, separate from your advocacy? Mm-hmm. How are you planning to meet the changes that may come? I mean, for example, a simple sort of thought in someone's head is, well, I could move to a certain area. Like if I live in Miami, South Florida, I should get out and I should move to some other place.
Yes. I would not buy beachfront property in Miami.
Right. And they have the limestone also, where the water comes up right to the water table.
Yes.
They can't even put dams and sort of. Right. So, what would you do? What will you do? What are you planning to do in order to sort of, deal with the unpredictability of this situation?
So sometimes that's terrifying, and I think that anybody who's a parent is occasionally terrified by what lies in store for their children. But, we choose to do things that I think are, sustainable. So we choose to live in New York City. We live in a multi-unit apartment block with solar panels on the roof and, good insulation and with very, very low electricity bills. So that's a good thing. We don't have a car. We don't need a car. We don't eat very much meat, no meat at all. And, we kind of think about the consequences of our actions. Now, the one caveat to that is that for whatever work purposes and going to conferences and things, I fly more than your average bear. And, in terms of my carbon footprint, that's the biggest thing that I do.
But those are things, that's like the Gandhi, be the change you wish to see in the world.
Yeah.
That's sort of you being a responsible citizen. But as a private citizen, if your models are telling you that in, let's say, 30 years, I'm not saying this is the case, but in 30 years, there will be regular inundation of New York.
Right.
And you are looking at the political climate and you are looking at the commercial climate and you're saying, okay, there's nothing going to stop this. You're going to leave New York. That's a perfect example, right? You're not going to stay in New York,
I'm also not buying riverside property in Red Hook. Right. So,
Right. But what I'm saying is,
we live.
you do live up on the Upper West Side, probably, right?
I live in Harlem.
Right, but you live. That's actually mountainous in relative to other areas of Manhattan.
Yeah, so it's not in one of the flood zones.
Right.
And I look at the flood zone maps. And I look at the flood zone maps in Miami. I look at them in DC. I look at them in New York. And I can't tell. People ask me all the time, should I buy a house there? Should I buy a I would not.
Where can people see flood zone? Where can people see these maps?
The New York City maps are all on the New York City website. Plan NYC was the old name for it. It might have changed within the de Blasio administration, but you can see all these things on the website of NewYorkCity.gov.
Is there a good resource in general, or a few good resources in general, for people that want to plan their lives? If you believe,
right.
If you look at the data and you understand that the climate is warming and there will be repercussions regardless of what we do now, and you want to understand what those probability functions are there good resources for people on an individual basis to plan their lives?
Yeah. So, if you live near a river or a floodplain, you should know about it. And FEMA has maps, and they're not always totally up to date, and they can fool you if you're quite close to the edge. There's a number of sites where you can go in and you can put a sea level rise amount and you can see how close your house is to the high tide zone. Those are useful to find. I can't remember the site offhand, but I can give you the link afterwards. But
we're talking about, of course, I'd love for you to give me anything that I could share with our audience, because I think this is actually really practical. But also, these are complex phenomena, right? So you could be, is it great to go move to Norway? Not that you could easily get citizenship in Norway, but those are sort of obvious things. But at the same time, there are these non-linearities. You could say, okay, I'll move to Colorado, but then let's say the supply chain for food in Colorado gets disrupted based on the climate change.
No, but the problem is
so complex that
I can't predict any of that.
Exactly.
Right? The models that we have are models of the physical system. They're not models of the sociology of humans. They're not models of economies. They're not models of governance. They're not models of democracy. And so the kinds of things that we can model are not the answers that people need, right? Because that's what you want to know. Is like how is society going to react?
Right.
What's going to happen to supply chains? What's going to happen to transportation? What's the technology that's going to allow all these things to happen? And those aren't the kind of things that we know how to predict, right? You go back 100 years, could they have predicted how society has really worked out here? Right? No. There's so many contingent things. But they may have been able to work out what the climate was going to do, right? So people often assume that I'm some guru of the sociology of how people react to things, and I'm not. I'm a mathematician turned physicist and climate scientist, and I understand things like radiation and clouds and ocean circulation and sea ice and, vegetation feedbacks. But the important things, the key things, are the human feedbacks.
Right.
And I'm as much in the dark as anyone.
Well, on that note of humility, I hope we don't, I'm trying myself not to sort of be passive.
Right.
But of course it's very difficult. It's interesting. I'll just leave our audience with this. Last night I was listening to some audio. It might have been one of your sort of conversations on this. And I was driving, actually. I had gone away for the weekend. I was driving back into the city and it was pouring rain. and I was thinking about this, and I was getting anxious in a way that I don't normally ever become anxious. And I almost hydroplaned. And I said to myself, whoa, okay, there you go, like immediate risks, like, sort of recalculation. And I was relieved almost that I had that moment of recognition that I almost hydroplaned, because now is what matters. And then I went back to just being able to ignore this.
Yeah.
But when you spend time with this subject, my experience is that it is, there's some interesting esoteric subjects that we cover on this program, like goal setting and utility functions and artificial intelligence and engineering, et cetera, disease, vectors as a result of antibiotic resistance, et cetera. But this has been the most upsetting, and that's the word I would use. I would just say it's upsetting in a way that, and anxiety-provoking in a way that is unique.
So I don't think it needs to be. But you do need to understand that you've got two kinds of problems. You've got your acute problems, things that demand your attention right now. You break your arm, you hydroplane, you have you crash your car. All of these things are very immediate problems that exclude everything else while you deal with those things. And then you've got chronic problems. And climate change is a chronic problem. It's something that's just like building slowly day after day after day. But we do deal with chronic problems all the time. Right? The fact that we're getting older, the fact that people have diabetes, the fact that you have high cholesterol, that you don't exercise enough, or that you need to save for your retirement. All of these things are long-term chronic issues that you have to deal with. And we manage that. We do manage that. We manage to get a mortgage and pay it off after 30 years. We can think in long terms. We can lose weight. We can reduce our cholesterol. Right? Climate change is another one of those problems. And I think part of the problem that we've had in how people talk about it is that people confuse it with an acute problem, with having broken their arm, and there has to be an urgent response. And then when nothing happens, then people think, well, okay, well, maybe it wasn't that urgent, but all the time it's kind of building and building and building and building and building. You have to recognize the nature of the problem if you're going to come close to finding sustainable ways to deal with it. And I'm not just talking about sustainability. I'm just talking about having conversations that can be sustainable for the decades that it's going to take to deal with this problem.
Dr. Schmidt, thank you so much for coming on the program. And I hope to put a list of reading materials on our website for our audience as well after this, that maybe you can sort of give me a few good recommendations.
I'd love to. Thank you very much.
Thanks for coming on the program.
Thank you.
And that was my episode with Gavin Schmidt. I want to thank Dr. Schmidt for being on my program. Today's episode was produced by me and Genevieve Annable. Edits and engineering are Stylianos Nicolaou. For more episodes, you can check out our website at hiddenforcespod.com. Join the conversation through Facebook, Twitter, and Instagram at Hidden Forces Pod, or send me an email at dk@hiddenforcespod.com. Thanks for listening. We'll see you next week.